to do polynomial division. But we're going to use a method I just learned a few days ago, exploding dots. And James Tanton is this gentleman from Australia. So if you ever want to see like a very detailed explanation of how he built this, because you can do normal division this way, you can look him up. He's got some good explanations. But I'm going to do a really simplified version to compare it to synthetic division. So what he's done is he builds a box. Think of it like a die. You ever played dice before? You know how dice have like two boxes and there's dots in there kind of thing. We're going to be using that same kind of concept. We're going to have a box for every single term in our polynomial. So there's four. So we're going to 1, 2, 3, 4 terms. And think of this as like, this is the constant. So this is the 1. These are the x's to the power of 1. This is your x to the power of 2. These are your x to the power of 3. That's how you know how to fill those in. This is very much doing theoretical math with manipulatives. So now we take the coefficients from each and we fill them in. Well, there's a coefficient of 1, so there'd be 1 dot here. That's where we get the concept of dots. There are 2 dots here. -6, we're going to represent it as just kind of hollow dots, okay? So we draw 6 hollow dots there, and 1 constant. Wonderful. What are we dividing by? Well, we're dividing by x plus 2, so we're going to build a die. Remember, here's our constant, and here's our x to the power of 1. Well, there are 2 constants and 1x. What we're going to try to do is find this relationship, a dot, and then 2 dots in the next column, all the way through here. So, when I take a look, is there 1 dot and then 2 dots? Works out great. So we put the value of 1. Okay, I'm just going to use tallies, and we can count tallies. So think that as a tally of 1. I go to the next one. Are there anything in here? No. So I'm going to put nothing here. And if you remember, we did this question previously. There ends up being 0 there. So now we're going to move to this one. But now we run into a bit of a problem. We have negatives, and these are whole numbers. So what we're going to have to do is create whole numbers so that we can, or we can do the anti-dots. So in order to do this, for each term we put in here, we need to have an anti-dot. So because there's an equivalent of this, let's say, is you are also looking for this. See how they're hollow? So we're going to try to find that relationship here. Well, we need anti-dots in order to do that. So for every dot, we need at least 2 anti-dots, right? That's what this relationship is. It's a 1 dot in the left column and then 2 anti-dots in the other. So I'm going to put 2 anti-dots. Every time you do that, to balance it, you remember completing the square, you have to put 2 whole dots. Think of it like balancing in space. Like antimatter and real matter. You have to balance. So when I do that, here we go. I get one set of 1 and 2. Okay. Okay, I got to do another set, so I got to make 2 more anti-dots, which means I need 2 more full dots. And clearly I need a much bigger box for this. It's going to get pretty big pretty fast. There's another relationship. So I'm going to keep building these dots and anti-dots, okay? So I'm going to build 2 more, which means 2 more whole dots, 2 more anti-dots. I'm just going to try to speed this up a bit. So now we're getting this relationship here. There's 2. There's 2. It looks like we need 2 more of them. I should have made a much bigger space for this. I'm going to build 2 more anti-dots, which means I need 2 more whole dots, 2 more anti-dots, 2 more whole dots. And I've now done, there's a relationship, and there's another relationship. So, kind of messy. How many did I do? Well, I did 1, 2, 3, 4, 5, 6. I ended up doing 6 of them, and technically these were the negative versions of that. Okay, so I'm going to put 6 tallies, 1, 2, 3, 4, 5, 6, which means it represents the number 6. But technically you're negative, so always keep in mind that these are negative. So maybe I'll put in another color, red, representing our negative values, okay? So with that being said, here are our tallies. There's 1 tally in the x squared, so I'm going to put 1x squared, okay? There were 0 tallies in our x's, so I'm going to say plus 0x, okay? And there were 6 negative tallies in our constant, so I'm going to put -6. And if you recall, that's what the division answer was, okay? But what else I do have is, can we count this here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I have 13 remaining dots. There is nothing I can do. So we say plus 13. So if you were to take this equation and divide it, this is what you would get. And we could rewrite this whole function. If you recall in the last time we did this question, it would be the same as saying x plus 2 multiplied by x squared. We don't need to write that 0 in. Minus 6 plus remainder 13. Okay? This, I know a little confusing, is a visual way to go through these polynomial division. You want me to do another one quickly with you? Try it again? Here. Let's